Learning objectives. In this chapter, the user would learn the following aspects of finite state machines and languages. Representation of special languages and grammars, finite state machines, semigroups, machines and languages, machines and regular languages, simplification of machines. Introduction. Words in the English language can be combined in various ways. The grammar of English tells us whether a combination of words is a valid sentence. For instance, the frog writes neatly is a valid sentence because it is formed from a noun phrase. The frog made up by the article, the, and the noun frog followed by a verb phrase writes neatly, made up of the verb writes and the adverb neatly. We do not care that this is a nonsensical statement because we are concerned only with the syntax or form of the sentence and not its semantics or meaning. We also note that the combination of words swims quickly. Mathematics is not a valid sentence because it does not follow the rules of English grammar. The sentence of a formal language using a grammar. Use of grammars helps when we consider the two classes of problems that arise most frequently in applications to programming languages. How can we determine whether a combination of words is a valid sentence in a formal language? How can we generate the valid sentences of a formal language before giving a technical definition of a grammar? We will describe an example of a grammar that generates a subset of English. This subset of English is defined using a list of rules that describe how a valid sentence can be produced. We are shown in the figure very clearly. Definition. A vocabulary or alphabet V is finite, non-empty set of elements called symbols. A word or sentence after V is a string of finite length of elements of V. The empty string or null string, denoted by lambda, is a string containing no symbols. The set of all words over V is denoted by V. A language over V is a subset of V star. A phrase structure grammar G equal to V, T, S, P consists of a vocabulary V, a subset T of V consisting of terminal symbols, a start symbol S from V, and a finite set of productions P. The set V minus T is denoted by N. The elements of N are called non-terminal symbols. Every production in P must contain at least one non-terminal on its left side. Types of phrase structure grammars. Phrase structure grammars can be classified according to the types of productions that are allowed. We will describe the classification scheme introduced by Noam Chomsky. We will see that the different types of languages defined in this scheme correspond to the classes of languages that can be recognized using different models of computing machines. A type 0 grammar has no restrictions on its productions. A type 1 grammar can have productions of the form W1 tends to W2 where W1 equal to 1 AR and W2 equal to 1 WR. Where A is a non-terminal symbol where 1 and R are strings of 0 or more terminal or non-terminal symbols and W is a non-empty string of terminal or non-terminal symbols. It can also have the production S tends to lambda as long as S does not appear on the right hand side of any other production. A type 2 grammar can have productions only of the form W1 tends to W2 where W1 is a single symbol that is not a terminal symbol. A type 3 grammar can have productions only of the form W1 tends to W2 with W1 equal to A and either W2 equal to AB or W2 equal to A where A and B are non-terminal symbols and A is a terminal symbol, or with W1 equal to S and W2 equal to lambda. Type 2 grammars are called context-free grammars because a non-terminal symbol that is the left side of a production can be replaced in a string whenever it occurs, no matter what else is in the string. A language generated by a type 2 grammar is called a context-free language. When there is a production of the form 1W1R tends to 1W2R but not of the form W1 tends to W2, the grammar is called type 1 or context sensitive because W1 can be replaced by W2 only when it is surrounded by the strings 1 and R. A language generated by a type 1 grammar is called a context sensitive language. Type 3 grammars are also called regular grammars. A language generated by a regular grammar is called regular. The relation between regular languages and finite state machines. Derivation trees. A derivation in the language generated by a context-free grammar can be represented graphically using an ordered rooted tree called a derivation or phrase tree. The root of this tree represents the starting symbol. The internal vertices of the tree represent the non-terminal symbols that arise in the deviation. The leaves of the tree represent the terminal symbols that arise if the production A tends to W arises in the derivation where W is the word. The vertex that represents A as a children vertices that represent each symbol in W in order from left to right. Backus newer form. There is another notation that is sometimes used to specify a type 2 grammar called the Backus newer form, BNF. The specification of the programming language ALGOL, that is called ALGOL. The production in a type 2 grammar have a single non-terminal symbol as the left-hand side. Instead of listing all the productions separately, the same non-terminal symbol on the left-hand side into one statement. Instead of using the symbol in a production, strings and languages, vocabulary V. A finite set of symbols, example V equal to 0, 1. String W, a finite sequence of symbols from V, example W1 equal to 0, 1, 0 and W2 equal to 1, 1, 1, 1, 0. Empty string lambda. The string of length 0. Concatenation VW. VW string V, then string W, Wn. String W repeated n times. Example 0 cube equal to 0, 0, 0. V star, all possible strings as V. Language L, a subset of all possible strings V star. Example L equal to 1 power m, 0 power n, such that m belongs to n and n belongs to n. Phrase structure grammars. A phrase structure grammar G consists of vocabulary V divided into two subsets, terminal symbols T and non-terminal symbols N. Start symbols S belongs to N. A finite set of productions P. Each production has the form X tends to Y, where X belongs to V plus and Y belongs to V star. This means we can derive string U, Y, V from string UXZ. A string W is an element of the language generated by G if W can be derived from S by applying a sequence of productions. Alphabets and languages. Definition. A vocabulary or alphabet V is finite, non-empty set of symbols. A word or sentence over V is a finite string of symbols from V. The empty string or null string denoted by 1 is a string containing no symbol. Set of all words over V is denoted by V star. A language over V is a subset of V star. Language examples. Let V equal to 0, 1. 0, 0, 1, 1, 0. 1, 1, 1, 1, 1. 0, 0. And 1, 1 are words over V. 0, 1, 2. A, 2, 3, 4. And 2, 2, 2 are not words over V. V star equal to 0, 1, 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, 0, etc. In other words, V star is the set of all binary strings. The set of strings consisting of only zeros is a language over V star. 1, 1, 0, 1, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 0, etc. is a language over V star. Concatenation. Definition. Let V be a vocabulary and A and B be subsets of V star. The concatenation of A and B, denoted by AB, is a set of all strings of the form XY, where X belongs to A and Y belongs to B. Example, let A equal to 0, 1, 0 and B equal to 1, 1, 2. Then AB equal to 0, 1, 0, 1, 2, 1, 0, 1, 1, 0, 1, 2. Then BA equal to 1, 0, 1, 1, 0, 1, 2, 0, 1, 2, 1, 0. Then AA equal to 0, 0, 0, 1, 0, 1, 0, 0, 1, 0, 1, 0. AAA equal to A into AA equal to 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 0, 0, 0, 1, 0, 0, 1, 0, 1, 0, 1, 0, 0, 1, 0, 1, 0, 1, 0. Concatenation A power n. Definition. Let V be a vocabulary and a subset of V star, then A power 0 equal to lambda, and for n greater than 0, we can define A power n equal to A power n minus 1 into A. Example, let A equal to 0, 1, 0, then A power 0 equal to lambda, A power 1 equal to AOA equal to lambda into A equal to 0, 1, 0. A square equal to A1A equal to 0, 0, 0, 1, 0, 1, 0, 0, 1, 0, 1, 0. A cube equal to A2A equal to 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 0, 0, 0, 1, 0, 0, 1, 0, 1, 0, 1, 0, 0, 1, 0, 1, 0, 1, 0. Kleene closure. Definition. Let V be a vocabulary and A be a subset of V star. The Kleene closure of A, denoted by A star, is a set consisting of concatenations of an arbitrary number of strings from A, that is A star equal to union K equal to 0 to infinity A power K. Definition. A plus is a set of non-empty strings over A. In other words, A plus equal to union K equal to 1 to infinity A power K equal to A star minus lambda. Example, let A equal to 0, 1, then A power 0 equal to lambda, A1 equal to 0, 1, A square equal to 0, 0, 0, 1, 1, 0, 1, 1. A cube equal to 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Then A star equal to 0, 1 star equal to all binary strings. Let B equal to 1, 1, 1. Then B power 0 equal to lambda. B power 1 equal to 1, 1, 1. B square equal to 1, 1, 1, 1, 1, 1. B cube equal to 1, 1, 1, 1, 1, 1, 1, 1, 1. B star is the set of strings with 3n ones for every n greater than or equal to 0. Regular sets. Definition. A regular set is a set that can be generated starting from the empty set, empty string, and a single elements from the vocabulary using concatenations, unions, and Kleene closures in arbitrary order. We will give you a more precise definition after we define a regular expression. Properties of regular sets. Pumping, lemma for regular sets. Applying pumping lemma. Closure properties of regular sets. Emptiness of L of M. Finiteness of L of M. Equivalence of two FAS. Properties of regular sets. Example, closed under union, concatenation, and Kleene closure. Closed under complementation. If L is regular, then summation star minus L is regular. Intersection, L1 intersection L2 equal to L1 bar union L2 bar whole bar. Regular expressions. Definition. The regular expressions over a set 1 are defined recursively by pi. the empty set, is a regular expression. Lambda, the set containing the empty string, is a regular expression. X is a regular expression for all x belongs to 1. AB, A union B, and A star are regular expressions if A and B are regular expressions. Definition: a regular set is a set represented by a regular expression. Examples: 0, 0, 1, star, 1 of 0 union 1, 0, 0 union 1 star 1, 1, and AB star C are regular expressions. The regular set defined by the regular expression 0, 1 star is the set of strings starting with a 0 followed by 0 or more ones. The regular set defined by 1, 0 star is a set of strings containing 0 or more copies of 1, 0. The regular set defined by 0, 0 union 1 whole star 1 is the set of all binary strings beginning with 0 and ending with 1. The regular set defined by 0 union 1, 1, 0 union 1 is the set of strings 0, 1, 0, 0, 1, 1, 1, 1, 0, 1, 1, 1. Regular expression applications. Regular expressions are actually used quite often in computer science. For instance, if you are editing a file with VI and want to see if it contains a string blah followed by a number followed by any character followed by the letter Q, you can use the regular expression blah 0 to 9, 0 to 9 star dot Q. This works because VI uses regular expressions for searching. Finite state of machines. Many kinds of machines, including components in computers, can be modeled using a structure called a finite state machine. Several types of finite state machines are commonly used in models. All these versions of finite state machines include a finite set of states with a designated starting state, an input alphabet, and a transition function that assigns the next state to every state, and input pair. Finite state machines are used extensively in applications in computer science and data networking. For example, finite state machines are the basis for programs for spell checking, grammar checking, indexing or searching large bodies of text, recognizing speech. A vending machine accepts nickels 5 cents, dimes 10 cents, and quarters 25 cents. When a total of 30 cents or more has been deposited, the machine immediately returns the amount in excess of 30 cents. When 30 cents has been deposited and any excess refunded, the customer can push an orange button and receive an orange juice or push a red button and receive an apple juice. We can describe how the machine works by specifying its states, how it changes states when input is received, and the output that is produced for every combination of input and current state. We have shown in the table next state, output, and then state, input, output. We can easily see how we explained in the table. The machine can be in any of 7 different states Si, I equal to 0, 1, 2, etc. 6, where Si is the state where the machine has collected 5 I cents. The machine starts in state S0 with 0 cents received. The possible units are 5 cents, 10 cents, 25 cents, the orange button O and the red button R. The possible outputs are nothing, N, 5 cents, 10 cents, 15 cents, 20 cents, 25 cents, an orange juice and an apple juice. Suppose that a student puts in a dime followed by a quarter, receives 5 cents back, and then pushes the orange button for an orange juice. The machine starts in state S0. The first input is 10 cents, which changes the state of the machine to S2 and gives no output. The second input is 25 cents. This changes the state from S2 to S6 and gives 5 cents as output. The next input is the orange button, which changes the state from S6 back to S0 because the machine returns to the start state and gives an orange juice as its output. Finite state machines with outputs. A finite state machine M equal to S, I, O, F, G, S0 consists of a finite set S of states, a finite input alphabet I, a finite output alphabet O, a transition function F that assigns to each state, and input pair a new state, an output function g that assigns to each state, and input pair an output, and an initial state s0. Let M equal to SIOFG S0 be a finite state machine. We can use a state table to represent the values of the transition function f and the output function g for all pairs of states and input. We previously constructed a state table for the vending machine discussed in the introduction to this section. Phrase structure grammars. Example: the state table shown in table 2 describes a finite state machine with s equal to s0, s1, s2, s3, I equal to 0, 1 and o equal to 0, 1. The value of the transition function f are displayed in the first two columns and the values of the output function g are displayed in the last two columns. Another way to represent a finite state machine is to use a state diagram, which is a directed graph with labeled edges. In this diagram, each state is represented by a circle. Arrows labeled with the input and output pair are shown for each transition. Table 2. Table 2 explains very clearly what we discussed in the above. Let M equal to SIOFG S0 be a finite state machine and L is a subset of I star. We say that M recognizes or accepts L if, example, produce a finite state machine that adds two positive integers using their binary expansions. Solution: when xn etc. x1 x0 into 2 and yn etc. y1 y0 into 2 are added, the following procedure is followed. First, the bits x0 and y0 are added, producing a sum bit z0 and a carry bit c0. This carry bit is either 0 or 1. Then the bits x1 and y1 are added, together with carry c0. This gives a sum bit z1 and a carry bit c1. This procedure is contained until the nth stage, when xn, yn and the previous carry cn-1 are added to produce the sum bit zn and the carry bit cn, which is equal to the sum bit zn plus 1. In certain coding scheme, when 3 consecutive ones appear in a message, the receiver of the message knows that there has been a transmission error. Construct a finite state machine that gives a 1 as its current output bit if and only if the last 3 bits received are all 1s. The state S1 remembers that the previous input was a 1, but the input before the previous input, if it exists, was not a 1. The state S2 remembers that the previous 2 inputs were 1s. An input of 1 takes S0 to S1 because now A1 and not 2 consecutive ones has been read. It takes S1 to S2 because now 2 consecutive ones has been read. And it takes S2 to itself because at least 2 consecutive ones have been read. An input of 0 takes every state to S0 because that breaks up any string of consecutive ones. The output for the transition from S2 to itself when a 1. One of the most important applications of finite state machines is in language recognition. This application plays a fundamental role in the design and construction of compiler for programming languages. A finite state machine with output can be used to recognize a language by giving an output of 1 when a string from the language has been read and a 0 otherwise. However, there are other types of finite state machines that are specially designed for recognizing languages instead of producing output. These machines have final states. A string is recognized if and only if it takes the starting state to one of these final states. Set of strings. The operations that will be defined here will be used extensively in our discussion of language recognition by finite state machines. Suppose that A and B are subsets of V star, where V is a vocabulary. The concatenation of A and B, denoted by AB, is the set of all strings of the form XY, where X is a string in A and Y is a string in B. Finite state machines with no output. Example, let A equal to 0, 1, 1 and B equal to 1, 1, 0, 1, 1, 0 Find AB and BA. Solution. The set AB contains every concatenation of a string in A and a string in B. Hence, AB equal to 0, 1, 0, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 1, 1, 0, 1, 1, 1, 1, 0. The set BA contains every concatenation of a string in B and a string in A. Hence, BA equal to 1, 0, 1, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 1, 1. Note that it is not necessarily the case that AB equal to BA when A and B are subsets of B, where B is an alphabet, as example 1 illustrates. From the definition of the concatenation of two sets of strings, we can define AN for n equal to 0, 1, 2, etc. This is done recursively by specifying that A power 0 equal to lambda, A power n plus 1 equal to A power n into A for n equal to 0, 1, 2, etc. Example, let A equal to 1, 0, 0. Find A power n for n equal to 0, 1, 2 and 3. Solution. We have A power 0 equal to lambda and A power 1 equal to AOA equal to lambda into A equal to 1, 0, 0. To find A square, we take concatenations of pairs of elements of A. This gives A square equal to 1, 1, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0. To find A cube, we take concatenations of elements in A square and A. This gives A cube equal to 1, 1, 1, 1, 1, 0, 0, 1, 0, 0, 1, 1, 0, 0, 0, 0, 0, 0, 1, 1, 0, 0, 1, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0. Suppose that A is a subset of B star, then the Kleene closure of A, denoted by A star, is the subset consisting of concatenations of arbitrarily many strings from A, that is, A star equal to UK power infinity equal to 0 into AK. Example, what are the Kleene closures of the sets A equal to 0, B equal to 0, 1 and C equal to 1, 1? Solution. The Kleene closure of A is the concatenation of the string O with itself an arbitrary finite number of times. Hence, A star equal to ON, n equal to 0, 1, 2, etc. The Kleene closure of B is the concatenation of an arbitrary number of strings where each string is either 0 or 1. This is the set of all strings over the alphabet B equal to 0, 1, that is B star equal to B star. Finally, the Kleene closure break of C is the concatenation of the string 1, 1 with itself an arbitrary number of times. Hence, C star is the set of strings consisting of an even number of ones. That is, C star equal to 1 power 2n such that n equal to 0, 1, 2, etc. A finite state machine with no output, such machines are also called finite state automata, and that is the terminology we will use for them here. Note, the singular of automata is automaton. These machines differ from the finite state machines studied in that they do not produce output, but they do have a set of final states. Recognize strings that take the starting state to a final state. A finite state automaton M equal to S I F S naught F consists of a finite set S of states, a finite input alphabet I, a transition function F that assigns a next state to every pair of state and input, so that F S cross I tends to S, an initial or start state S naught, and a subset F of S consisting of final or accepting states. A string X is said to be recognized or accepted by the machine M equal to S I F S naught F. if it takes the initial state S0 to a final state, that is, f of S0, x is a state in F. The language recognized or accepted by the machine M, denoted by L of M, is the set of all strings that are recognized by M. Two finite state automata are called equivalent if they recognize the same language. Non-deterministic finite state automata. A non-deterministic finite state automaton, M equal to SIF S0 F, consists of a set S of states, an input alphabet I, a transition function F that assigns a set of states to each pair of state and input so that F S cross I tends to P of S, a starting state S0 and a subset F of S consisting of the final states. Language recognition. Finite state automata can be used as language recognizers. What states can be recognized by these machines? Although this seems like an extremely difficult problem, there is a simple characterization of the sets that can be recognized by the finite state automata. This problem was first solved in 1956 by the American mathematician Stephen Kleene. A finite state automaton that recognizes a set if and only if this set can be built up from the null set, the empty string and the singleton strings by taking concatenations, unions, Kleene closures in arbitrary order. Sets that can be built up in this way are called regular sets. The regular expressions over a set I are defined recursively by the symbol pi is a regular expression, the symbol lambda is a regular expression, the symbol x is a regular expression where x belongs to I, the symbol AB, A union B and A star are regular expressions whenever A and B are regular expressions. Each regular expression represents a set specified by these rules. Pi represents the empty set, that is the set with no strings. Lambda represents the set lambda, which is the set containing the empty string. X represents the set X containing the string with one symbol X. AB represents the concatenation of the sets represented by A and by B. A union B represents the union of the sets represented by A and by B. A star represents the Kleene closure of the set represented by A. The finite state automata cannot be used as general models of the computation. They are limited in what they can do. For example, finite state automata are able to recognize regular sets but are not able to recognize many easy to describe sets including 0n, 1n, such that n greater than or equal to 0, which computers recognize using memory. We can use finite state automata to compute relatively simple functions such as the sum of two numbers, but we cannot use them to compute functions that computers can, such as the product of two numbers. To overcome these deficiencies, we can use a more powerful type of machine known as a Turing machine, after Alan Turing, the famous mathematician and computer scientist who invented them in the 1930s. Turing machines. A Turing machine consists of a control unit which at any step in one of the finitely many different states, together with a tap divided into cells which is infinite in both directions. Turing machines have read and write capabilities on the tape as the control unit moves back and forth along this tape, changing states depending on the tap symbol read. Turing machines are more powerful than finite state machines because they include memory capabilities that finite state machines lack. We will show how to use Turing machines to recognize sets, including sets that cannot be recognized by finite state machines. Definition of Turing machines. A Turing machine T equal to Si. F S0 consists of a finite set S of states and alphabet I, containing the blank symbol B, a partial function f from S cross I to S cross I cross R, L, and a starting state S0. Definition of Turing machines. To interpret this definition in terms of a machine, consider a control unit and a tap divided into cells infinite in both directions, having only a finite number of non-blank symbols on it at any given time. The action of the Turing machine at each step of its operation depends on the value of the partial function f for the current state and tap symbol. At each step, the control unit reads the current tape symbol x if the control unit is in state s and if the partial function f is defined for the pair s, x with f of s, x equal to s power 1 x power 1 d. The control unit enters the state s dash. Write the symbol x1 in the current cell, erasing x and moving right one cell if d equal to r, or moves left one cell if d equal to l. Using turning machines to recognize sets. Turning machines can be used to recognize sets. To do so requires that we define the concept of a final state as follows. A final state of a turning machine T is a state that is not the first state in any phi tuple in the description of T using phi tuples, for example state S0 in example 1. Machine halts. We can now define what it means for a turning machine to recognize a string. Given a string, we write consecutive symbols in the string in consecutive cells. Definition. Let V be a subset of an alphabet T. A turning machine T equal to SIF S0 recognizes a string X in V star if and only if T, starting in the initial position when X is written on the tape, halts in a final state. T is said to recognize a subset A of V star if X is recognized by T, if and only if X belongs to A. Find a turning machine that recognizes the set of bit strings that have a 1 as their second bit. That is, the regular set 0 union 1, 1, 0 union 1 star. Solution. A turning machine that, starting at the leftmost non-blank tap cell, moving right and determines whether the second symbol is a 1. If the second symbol is 1, the machine should move into a final state. If the second symbol is not a 1, the machine should not halt, or it should halt in a non-final state. To construct such a machine, we include the phi tuples S0, O, S1, O, R and S0, 1, S1, 1, R to read in the first symbol and put the turning machine state S1. Next we include the phi tuples S1, O, S2, O, R and S1, 1, S3, 1, R to read in the second symbol and either move to state S2 if the symbol is a O or to state S3 if the symbol is a 1. We do not want to recognize strings that have a 0 as a second bit. S0, S2 should not be a final state. Definition of turning machine. A turning machine can be thought of as a computer that finds the values of a partial function. To see this, suppose that the turning machine T, when given the string x as input, halts with the string y on its tape. We can then define T of x equal to y. The domain of T is the set of strings for which T halts. T of x is undefined if T does not halt when given x as input. Thinking of a turning machine as a machine that computes the values of a function on strings is useful. But how we can use turning machines to compute functions defined on integers, on pairs of integers, on triples of integers? Different types of turning machines. There are many variations on the definition of a turning machine. We can expand the capabilities of a turning machine in a widely variety of ways. For example, we can allow a turning machine to move right, left or not at all at each step. We can allow a turning machine to operate on multiple taps using 2 plus 3n tuples to describe the turning machine when n tapes are used. We can allow the tap to be two-dimensional where at each step we move up, down, right or left, not just right or left as we do on a one-dimensional tape. We can allow multiple tap heads that read different cells simultaneously. Furthermore, we can allow a turning machine to be non-deterministic by allowing a state tap symbol pair to possibly appear as the first elements in more than one phi tuple of the turning machine. Turning machines and its variants. Example, recognize the language 01 star and 10 star The machine remembers the first symbol read in its state. Solution. States are of the form Q0 Q1 into 0 1B. Q0 indicates the first symbol has not been read, Q1 that it has been, while 0 1B is the data portion that remembers the first symbol. Initial state is Q0, B and the final state is Q1, B. Delta Q0, B A equal to Q1, A delta Q1, A dash Q1, A dash R, where A dash into 6 equal to A, delta Q1, B equal to Q1, B R. Shifting symbols problem. Solution. Remember the last case symbols in finite control. States are Q0 into K. Initial state is Q0, HB, B, etc. BI. Delta of Q0, HA1, etc. AI, B, etc. BI, A equal to Q0, HA1, etc. AI, A, B, etc. BI, B, R, where AJ6 equal to B and A6 equal to B. Delta of Q0, HA1, A2, etc. AKI, B equal to Q0, HA2, etc. AK, BI, A1R. When you finish reading the tab, write everything in your finite control and accept. Conclusion. In this chapter, the user have covered the following aspects of finite state machines and languages. Languages. Representation of special languages and grammars. Finite state machines. Semigroups, machines and languages. Machines and regular languages. Simplification of machines.